Hello everyone. So we looked at the Kolmogorov's hypothesis, all the three hypotheses last time. The local isotropy hypothesis, his first similarity hypothesis, and the second similarity hypothesis, which was the third hypothesis. So just quickly to restate those. The local isotropy hypothesis stated that you have these energy containing eddies, anisotropic energy containing eddies, and everything below that we consider that demarcation to be 1/6 L0. Everything below that are statistically isotropic. Second hypothesis was that the first on the small scales which are below this demarcation length scale of 1/6 L0 have a universal equilibrium range. They have a universal equilibrium range that is dependent on both viscosity and epsilon. Kinematic viscosity and epsilon. The third hypothesis, or the second similarity hypothesis, was that the small scales below 1/6 L0 and there is a range of length scales that is above LDI. We assumed it was 60 eta. So much larger than the Kolmogorov scale and much less than the largest length scale. So we call that the inertial subrange. In that range, the scales are dependent only on epsilon and not viscosity. The reason being, these are large eddies, so Reynolds number is high enough that viscosity does not play a role. These were the three hypotheses. And as a result, we derived some relationships for the in terms of the smallest length scale to the largest length scale, and the smallest length scale to the largest length scale, which was this one. And also in terms of the inertial subrange, we had derived this one. So U eta over UL, right? So UL, so the velocity scale associated with the length scales in the inertial subrange. So we derived all that. What's next? Let's now look at in terms of the transfer of energy. So I've shown the length scales again here. I have, the same usual suspects. I have these characteristic length scale, the largest length scale, and the demarcation length scale. Obviously, everything above LEI is the energy containing range. This is where the energy is being produced. So I am calling that the production. That energy is being transferred to the smaller scales. And you have everything below that is the universal equilibrium range. Remember? And I have LDI as a separation length scale, which is approximately 60 times eta. So everything between 60 eta and eta is the dissipation rate. So this is where the dissipation is happening. And this inertial subrange, it is only dependent on epsilon, isn't it? Here, entire thing is dependent on kinematic viscosity and dissipation rate. So I have production, I have dissipation, and in between I have transfer of energy, right? The transfer of energy, so I have the energy containing range. From that range, the energy gets transferred through the inertial subrange to the dissipation range, and there it dissipates. So this is the energy cascade, isn't it? So in the conception of energy cascade, your T of L is the rate at which energy is transferred from eddies larger than L to smaller than L, because it goes from the large length scale to the small length scale, isn't it? So let's assume TL is the rate at which energy is transferred from the scales that are larger than L to scales that are smaller than L. Now, if transfer process is accomplished primarily by eddies comparable to L, then TL is can be expected to be of the order of UL squared over tau L. What is this? Like dissipation. This transfer, you would think it is occurs at the same rate at which dissipation happens. We'll get to that in a bit. But this transfer, you would think it is comparable to kinetic energy over time. So that is why I'm writing it as UL squared over tau L. But we also know that UL squared, as in U of L squared over tau L is same as epsilon, which means that transfer is equal to epsilon, isn't it? We know that the dissipation happens at the rate at which the kinetic energy is getting transferred. So TL is the same as epsilon. This means that the TEI, which is the rate at which energy is being transferred from scales greater than LEI to scales less than LEI, is the same as, right? So that is what T of LEI is the same as TL, meaning the transfer that is happening through the inertial subrange, because L refers to an inertial subrange scale. And this T of L is the same as T of DI, which is the rate at which energy is being transferred into the dissipation range, or T of LDI. So that means what? It is the rate of transfer of energy from scales that are greater than LDI or 60 eta to scales that are less than LDI or 60 eta, which is the same as epsilon. So this entire transfer from the energy containing range to the inertial subrange to the dissipation range is all equal to epsilon. So and we obviously know that L is greater than LDI and it is less than LEI. It is the inertial subrange. So this is the rate at which energy is transferred from the large scales. And therefore, it is the dissipation range epsilon. That's the key takeaway here. This transfer of energy, we have now, we derived the the length scales last time. We derived the ratio of length scales last time. Now we are looking at it in terms of the energy cascade. The energy containing range, the production range, it all starts there. Energy gets transferred through the inertial subrange, through LDI into the dissipation range, and hence it is equal to epsilon. I hope this is clear now. So the next step would be to look at the energy spectrum and to think about how is the turbulent kinetic energy distributed across the eddies of different sizes. So this is a picture that I have shown earlier, again from Pope's book. These are measurements of the energy spectra from different kinds of data. I'll go into these kind of plots later, but what I want you to look at here is 2 or 3 things. One, on the y-axis I have the energy spectrum, which is scaled with some appropriate variables. Okay, it looks like it is scaled with epsilon and nu. Why that is the case, we'll come to that later. But it is scaled with epsilon and nu. And on the x-axis, I have the wave number, again scaled with the Kolmogorov scale. And what I have is, for the most part, there is a huge overlap in the different plots. This is not surprising considering what we now know about Kolmogorov's hypothesis. Kolmogorov said that everything in the small scales below the energy containing range, below LEI, has a universal form. And they are statistically identical if you scale it with the Kolmogorov scale. That is what we are doing here. We have scaled it with the Kolmogorov scale. So everything is overlapping on one single line. Isn't that amazing? So all these symbols, these different kinds of symbols that you're seeing are different kinds of turbulent flows. There's grid turbulence here, there's channel flow here, there's jet flow here, there's shear layers here. All are turbulent, by the way. The energy containing range is anisotropic, so they have a directional bias, as I was discussing earlier, and that is why these are very different. These are identical because you have scaled it with the Kolmogorov scale. They would have been similar if you had not scaled it. Because you have scaled it, they are identical. But the additional point I'm trying to make through this graph is that by trying to address this question, how is the turbulent kinetic energy distributed across the eddies? For that, what we need to do is, we need to think about the spectrum as some kind of a function. And now you have to start thinking differently from the length scales. Think of in terms of wave numbers, which is what the x-axis contained. It consisted of wave numbers. So I have to think of it in terms of wave numbers. So let's say the wave number is 2 pi over L. And that's how the wave number is defined. It is 2 pi over L. The important thing is it is the inverse of the length scale. And it is defined as 2 pi over L. That's how a wave number is defined. So if I want to find out the kinetic energy in the wave number range of Ka to Kb, if I want to find out the turbulent kinetic energy in the wave number range of Ka to Kb, what I am doing is I have to integrate the energy spectrum across that range. So that is Ka to Kb, Ek dk. Ek is the energy spectrum. Now, the symbol that I have used on the slide is kappa. I am just referring to it as kappa. I'm just referring to it as K. But this K, turbulent kinetic energy, within the range Ka to Kb. So essentially what I'm saying is, at a particular range, kappa A to kappa B, okay? At a particular range kappa A to kappa B, what I'm saying is, this is the kinetic energy. You integrate the energy spectrum function from kappa A to kappa B. Similarly, the dissipation in that range. So that means what? That is the energy that is dissipated in that range. Earlier, what I calculated was the turbulent kinetic energy in that range. Now I'm calculating the dissipation. The dissipation is given by kappa A to kappa B, 2 nu kappa squared E kappa d kappa. So remember, how this is derived is not important right now. For now, let's just take the dissipation as 2 nu kappa squared. The integral, the area under the curve, or the integral of the energy spectrum function is the turbulent kinetic energy. And the integral of 2 nu k squared times the energy spectrum function is the dissipation. Alright, so that's your definition for the turbulent kinetic energy and the dissipation. Now, from the first hypothesis, or first similarity hypothesis of Kolmogorov, that is the second hypothesis of Kolmogorov, we know that there is a universal equilibrium range below LEI, which means if you think of it in terms of wave number, there is a universal equilibrium range above KEI equivalent to 2 pi over LEI. So this is the wave number associated with the energy containing scale. So kappa greater than kappa EI, which is equal to 2 pi over LEI, the spectrum, it is a universal equilibrium range, so it depends on both epsilon and nu, which means your energy spectrum function should only depend on epsilon and nu, isn't it? Should only depend on epsilon and nu. Next, from the second similarity hypothesis, or his third hypothesis, Kolmogorov's third hypothesis, we know that in the inertial subrange, that is L less than LEI and L greater than LDI, so kappa less than kappa DI or kappa greater than kappa EI, and this is, by the way, equivalent to 2 pi over LDI. The spectrum is E kappa C epsilon to the 2/3 kappa to the minus 5/3. How did I get this? Because I know that the inertial subrange only depends on epsilon and it does not depend on nu. So there is a constant. There is obviously a constant there, and it would be epsilon to the 2/3 and kappa to the minus 5/3 in order to dimensionally match the energy spectrum. I know that it will only depend on epsilon. It would obviously depend on the independent variable, which is kappa, which is the wave number. So kappa would be there and epsilon would be there. That's it. So if I use those two, epsilon and kappa, I am going to get this function. Epsilon to the 2/3 and kappa to the minus 5/3. C is going to be a universal constant because it is a universal function. Now, let's think about this. Okay, so the fact that we got this to be kappa to the minus 5/3 is very interesting, isn't it? But let's try to make some sense out of it. Okay, so for that, let's consider the energy spectrum function to be, okay, some function a kappa to the minus 5/3. A is a constant, p is a constant. We don't know what p is, we don't know what a is yet. Now, if I want to find out the turbulent kinetic energy, so the energy contained in the wave number is greater than kappa, which means k to infinity, kappa to infinity. So I have k kappa to infinity is the integral of the energy spectrum function. So that is kappa to infinity e kappa prime d kappa prime. And if I integrate this, I just do a simple integration. I have a over p minus 1 kappa to the minus p minus 1. Now look at this function. This is only going to be valid for p greater than 1. What happens when p is less than 1? When p is less than 1, this number becomes negative. And negative of a negative number becomes positive. So then you have some number raised to a positive number which will diverge eventually. So for p less than 1, it is going to diverge, whereas for p greater than 1, it is going to converge. So this function is only valid for p greater than 1. Similarly, if I look at the dissipation, and again, dissipation happens towards the small scales. Energy, turbulent kinetic energy comes from the large scales. That is why I took kappa to the infinity. When I'm taking dissipation, I'm going to take 0 to kappa. Why? Because dissipation happens towards the smaller scales. Kinetic energy comes from the larger scales. The energy is produced. Production happens at the larger scales. Dissipation happens at the smaller scales. So when I take epsilon, which is the integral from 0 to kappa, I will take 0 to kappa only because the energy dissipates towards the smaller scales. Dissipation is happening at the smaller scales. So I have 0 to kappa, 2 nu kappa prime squared, e kappa prime, d kappa prime. And all I'm doing is I take kappa squared times this kappa to the minus p. So what I'm going to get here from here is that I'm going to get kappa to the minus p plus 2. Isn't it? I'm going to get kappa to the minus p plus 2. Then I integrate that. And then I get this. 2 nu a over 3 minus p kappa to the 3 minus p. It's a simple integration. You can do it. Now, if I look at 3 minus p, 3 minus p is going to be negative when p is greater, or 0 or negative when p is greater than 3. Greater than or equal to 3, I should say. So that means this integral is going to diverge for p is greater than or equal to 3. On the other hand, if p is less than 3, this is going to be a positive number. Here, this is going to be a positive number for p is less than 3. So in that sense, okay, in that sense, your equation is such that p has to be greater than 1 and less than 3. P has to be greater than 1 or less than 3. Remember, here you were considering p to be a negative number. Here you want p to be positive because the dissipation goes from 0 to kappa. So that is why we are saying it diverges for p is greater than or equal to 3. Whereas here we are considering it diverges for p is less than or equal to 1 because of the 3 minus p here. Here it is p minus 1. I hope that is clear. P minus 1, this becomes a this becomes a negative number. P minus 1 becomes a negative number when p is less than or equal to 1. Isn't it? It's 0 or a negative number. Let's say p is 0. Then it becomes minus 1. Minus of minus 1 becomes plus 1. Then you have kappa to the 1. It diverges. It keeps on increasing, isn't it? That's not what you want. You want an integral that converges for it to be consistent. Here, if I look at 3 minus p, what happens when p is greater than or equal to 3? So let's say p is equal to 4. Then I have 3 minus 4 minus 1. So here I want it to be a positive number because I am considering dissipation to be everything from 0 to kappa. I am considering dissipation to be very small from 0 to kappa. So that is why I want this to be a positive number. So thus p is a number between 1 and 3. So 5/3 does make sense. Between 1 and 3, 5/3 does make sense. So what we have is when we wrote earlier that E kappa is C epsilon to the 2/3 kappa to the minus 5/3. Okay, 5/3 does indeed make sense because it is a number between 1 and 3 that makes sure that the turbulent kinetic energy function, or the turbulent kinetic energy integral I should say, converges, and the dissipation integral converges. So K, turbulent kinetic energy kappa to infinity, and epsilon 0 to kappa, they converge. So that is what I have. So minus 5/3 does indeed make sense. So with p to the 5/3, k to the kappa to infinity is of the order of kappa to the minus 2/3 because it is kappa to the minus of p minus 1, isn't it? Because this is of the order of kappa to the minus p minus 1. So that is kappa to the minus, p is 5/3, so 5/3 minus 1, which is kappa to the minus 2/3. On the other hand, dissipation is kappa to the 3 minus p. So this is of the order of kappa to the 3 minus p. So that is kappa to the 3 minus 5/3. So that is kappa to the 4/3. So essentially what we are saying is with kappa equal to 5/3, the turbulent kinetic energy depends on kappa to the minus, is of the order of kappa to the minus 2/3, and the dissipation is kappa to the 4/3. So we know that this Kolmogorov minus 5/3 spectrum only applies to the inertial subrange, isn't it? We only took the inertial subrange because only there is the spectrum only dependent exclusively on epsilon and not nu. Because when we took the function, we considered it to be epsilon to the 2/3. We didn't consider a viscosity there. It only depended on epsilon and not nu because it was the inertial subrange. So that's what we mean here. Although the Kolmogorov minus 5/3 spectrum applies only to the inertial subrange, the observations made are consistent with the notion that the bulk of the energy is in the large scales, that is L greater than LDI, and the bulk of the dissipation is in the small scales, that is L less than LDI. Isn't it? Because you will see here that this kinetic energy is kappa to the minus 2/3. So most of the energy is coming from the large scales because it is kappa to the minus 2/3, right? Whereas if you look at epsilon, it is dependent on kappa to the 4/3. So as the wave numbers is increasing, this number is getting larger. As the wave numbers is decreasing, the kappa to the minus 2/3 is getting smaller. So most of the energy is coming from the smaller wave numbers or the larger length scales. Whereas most of the dissipation is concentrated in the smaller length scales or the larger wave numbers, because kappa to the 4/3 is becoming larger and larger as the wave number increases or the length scale decreases. I hope you understand this. Kappa to the 4/3 and kappa to the minus 2/3 gives us a lot of information. The fact that kappa to the 4/3 is becoming a larger and larger number as the wave number is increasing, as I'm going towards the dissipation range, tells me that the dissipation is concentrated in the smaller length scales or the larger wave numbers. The turbulent kinetic energy being proportional to kappa to the minus 2/3 tells me that as kappa is increasing, this value is going down. Whereas as kappa is decreasing, I am at the larger length scales and the smaller wave numbers, and this number is a large number. So it is telling me that most of the energy is contained in the large scales, whereas bulk of the dissipation happens at the small scales or the large wave numbers. I hope this was clear. So we will now look at the Kolmogorov hypothesis in the context of everything that we have learned so far, in the context of length scales and wave numbers, and restate those just to add some more clarity to it. Thank you.